Hello and welcome. These are the solutions to the remaining practice exam problems from our set of problems for our last lecture. These questions here on this slide come from chapter 9 on molecular orbital theory. So the first question here is asking us to consider C22 plus. So C22 plus is going to be 2 times 4 for carbon and then minus 2 for the 2 plus. So that's 6 electrons total. These are our 2 s orbitals. These are our 2 p orbitals, and this would be our sigma 2s, sigma star 2s, bonding, anti-bonding orbital. Our pi 2p come next, then our sigma 2p. The pi are the one that are doubly degenerate. There's 2 orbitals equal in energy. Our pi star 2p and our sigma star 2p for our anti-bonding orbitals for the ones that go up relative to their atomic orbital basis sets. And then this question here is getting at, putting 2 electrons here, 4, and then 6 electrons. Our bond order for C22 plus is going to be a half times, we're counting electrons, that's why we go half for the electron pair counting. So we go 2 plus 4 for 4 bonding electrons and then 2 anti-bonding electrons. And so these are the anti-bonding electrons here. And so this bond order is going to be equal to 1. O2, 2 minus, adding electrons to O2, so we use O2's diagram over here. And so for O2, that's going to be 2 times 6, and then plus 2 for the 2 minus charge, that goes to 14 electrons. Same 2s, 2p orbitals here. I don't really need to worry about filling electrons into the atom side. I'm just really trying to put my O2, 2 minus in the middle. And recognizing we go sigma 2s, sigma star 2s, and then sigma 2p, pi 2p. So notice the sigma's next, then the pi. And then our pi star 2p and our sigma star 2p orbitals. So we go 2, 4, 6, 8, 10, 12, 14. So for the bond order for O2, 2 minus, we have 2 plus 8 bonding electrons. So our bond order for O2, 2 minus, a half, and then 8 minus 2, 6 for 1 as well. So the bond order of both C22 plus and O2, 2 minus are equal to 1. And then we're asked number 15, for which molecule below is paramagnetic. Paramagnetic means it has at least one unpaired electron. And C22 plus is certainly paramagnetic. We have 2 unpaired electrons here. And then B2 is isoelectronic, has the same electron configuration. 6 electrons in, same configuration, same diagram, also would give us a paramagnetic molecule. So both 1 and 2 are paramagnetic. O2, if we kick 2 electrons off of O2, 2 minus, O2 would be paramagnetic as well, which is the correct property for O2. So these 2 questions here I pulled off of one of the practice final packets. The first one is just to kind of point out that these density questions you don't have to worry about. So we're telling you the size of some lattice and we're asking you to calculate a density, don't worry about doing those kinds of problems. So don't worry about calculating densities. If you're interested, they're in the book. They're tricky problems, but they're not ones that we're going to worry about solving. This one here I wanted to look at. This is like where I was getting at in class where where we can have more than one atom inside a unit cell and not necessarily have that atom be in the center of the box. And so let's just read the question. So rutile is a mineral comprised of Ti and oxygen. There are titanium atoms at each corner and a titanium atom in the center. So if we're counting titanium, we have atoms in the corner, that's 8 atoms times an eighth, and then plus the 1 in the center, so that's 2 titaniums. Then our oxygen is going to be, let's see what it says, 4 oxygen atoms are on the opposite faces of the cell. So we got 4 O's on faces times a half. Now notice that this isn't 6, just because of what we're told in the problem. 4 oxygens are on the opposite faces of the cell. So these look like, it's kind of hard to tell which ones are which, but it looks like there's ones in the face here and somewhere else. So there's 4 on the faces. And so the key is a face atom is being shared with one other unit cell. So an atom on the face, this atom is in this unit cell, the other half is on the unit cell on top of this box. And then it says there are 2 entirely within the cell. And it's hard to picture. This isn't the best picture in the world. But if we're picturing the 2 that look like they're in the cell, I think it's this one and this one. Look like they're like hanging out within the cell. It might actually be this one. It's really hard to see in the cell. But there's 2 O's that are totally in the cell. So 4 times a half is 2 plus 2, that's 4. So I got 4 oxygens here. So my formula should be Ti2O4. The empirical formula would be TiO2. So the simplest ratio would be TiO2. So the chemical formula should be the empirical formula of these ions. So TiO2. Lewis structure problem. Now, I wanted to point this problem out here just to give kind of a reminder that if you're asked to determine the best Lewis structure, there's 1 of 2 ways to think about this problem. One is just to do the normal Lewis structure. Just like come up with your Lewis structure based on our rules. So like single bond the O's, give the O's their octet, count the electrons up. We've only used 16, so there's 2 electrons left over to go on to sulfur. And then we have a 2+ formal charge, and octet's not yet filled, so let's make at least 1 double bond, kick this charge down to plus. And then if we wanted to, we could do this one too, where we come up with this Lewis structure as another viable Lewis structure. This one now has a 0 formal charge, minimizes the magnitudes of formal charge. So this is the formal charge rule Lewis structure, and this is the octet rule. So both of these are actually valid Lewis structures. One satisfies the octet rule for sulfur, the other one minimizes magnitudes of formal charge. Now, which of the following is the best Lewis structure? Like we can rule out some of these as not being the best just because maybe like in A, we don't have the lone pair on S. So we're deficient of 2 electrons. So this molecule here is actually SO2 with the 2+ charge. So we don't have the right charge shown, not the right number of electrons. So you can kind of look and see 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. This is SO2, 2 minus. This is not the right charge. So A and B are both wrong because they have the wrong number of electrons. C is wrong too. We're missing these electrons here. Doesn't have the right double bonds either. D is wrong because 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons, too many electrons as well. And then we get to E by one-way process of elimination. And then it also looks like the other resonance structure of our octet rule Lewis structure. So if this one had said this, if it looked like this structure here, that could be a best Lewis structure too. So there's 2 Lewis structures that could be best for SO2. For the choices here, E is the best answer since it's the only one that's possible. Now, if we wanted you to determine which of these 2 is better, well, we don't really know. We would say, if we want you to really determine the best Lewis structure, we would say just the one is the one that's the octet rule Lewis structure, the other one's the formal charge Lewis structure. What is the formal charge of phosphorus and PO4 3 minus where all the atoms obey the octet rule? So 5 plus 24 plus 3 is 32 electrons. So this is essential phosphorus. Oxygens all the way around. 4 total electrons around each O, or electron pairs around each O, so that's 32 electrons, no lone pair. Octet rule is being satisfied for phosphorus, and then we break the bonds in half. Phosphorus should have 5 electrons surrounding it for neutral charge, and it only has 4. So that's phosphorus with a net +1 charge. Which statement below is true about the resonance effect and the structure of ozone, in which 2 atoms are connected to a central O? This also has 18 electrons, like SO2 on the previous page. So this is just like SO2. This is one of the Lewis structures. And then the other resonance structure, we show this arrow. The arrow is meant to indicate that these electrons are resonating at all times. This isn't an equilibrium problem. This is an all-time problem where at all times, this is like this. And now if you think of the charge as alternating between 0 and -1 or -1 and 0, the charge on each O is -1/2. The bond orders here are either double or single. So we have 1, 2, 3 bonds being spread across the two covalent bonds between the O atoms. So this is a 3/2 bond. Okay, so let's look at some of the choices. Ozone contains 2 oxygen-oxygen bonds of different length. Incorrect. You may think that based off of one of the Lewis structures, but ozone never exists as one of these Lewis structures that we're sketching. A Lewis structure is a model. The model here for ozone says if we have 2 equivalent yet different Lewis structures, the real molecule at all times exists as the average of the composite due to delocalization of electron pairs. So electrons are delocalizing across that bond. Ozone contains 2 oxygen-oxygen bonds of equal length. Yes, because each of the bonds has an order of 3/2. Equal orders, equal length, so that's correct. The non-central oxygen atoms have a charge of -1/2. True, that's exactly true. The central O has a charge of plus. So we have 1, 2, 3, 4, 5 electrons surrounding each O. 6 minus 5 is +1. So +1 for the central O, and then and both of them the same. And then the outer O's, the non-central O, is -1/2. So that statement is true. So statements B and C are correct. Now let me say this in terms of the way you count pi system electrons. So the pi system electrons would be these 2 electrons here come into this bond. These 2 electrons leave. So we have 4 pi system electrons. But we have 2 electrons delocalized in the pi system. Totally different questions. To be honest, I argue with my colleagues about this because they don't seem to understand the difference between the two ideas. That the pi system are all the electrons involved in the pi system, and then the delocalized electrons are the electrons actually delocalized in the bond. It's like this extra electron pair that's being delocalized over to here. And so you can count those 2 electrons as being the delocalized pi electrons. If you had 4 delocalized pi electrons, then this molecule would have a bond order of 2, and you'd have double bonds on both those. That's not what we have here. So we have just 2 electrons that are delocalized at any time through the total system of 4 pi electrons. To be honest, I don't know why that number matters to anybody. Like, it doesn't mean a whole lot. This number means a lot more for something like this molecule here. If we step back to benzene, this was like one of the test questions from midterm 3 that gave some people an issue that this molecule moving to here, it's these electrons move to here, these electrons move to here, these electrons move to here. That's 6 pi system electrons. If you notice in the other structure that they've moved over, that those are the same electrons. Then it's not 12 because these are the electrons that were here. Just like we don't count these two, and then over to here and double count them again. So we don't say 8 for ozone. We still say 4 pi system, 2 electrons being delocalized. The only thing that's interesting here for benzene is you have 6 pi system electrons and you also have 6 electrons delocalized. The delocalized electrons are the electrons that are actually at any given moment spread across multiple bonds. So a localized bond means we have a bond here. So this is a localized double bond. That bond is between carbon and oxygen. So localized, the bond is exactly where we think it is. A delocalized bond is something like in carbonate, where we have that bond delocalizing here and here. So a delocalized bond is one that spreads itself out across multiple bonds. So this is a delocalized bond. Now, for carbonate, you get 2, 4, and then 6 electrons in the pi system, but there's only ever 2 delocalized pi electrons. Like in the pi system itself, or in the number of electron pairs that are actually in an orbital that holds those delocalized pi electrons at any given moment, it's only 2 electrons. So carbonate has 6 pi system electrons, but 2 electrons are delocalized. So these are two different numbers correspond to two different values, two different things, two different meanings. Okay, to be honest, I don't know if it's going to be that big of a deal in the final for counting these pi system electrons, but it just was an issue on midterm 3 that I'm sure a few of you guys may have still had some lingering questions about. All right, so moving on from here, so 45, these are just taken from some random practice exam packets. From VSEPR theory, what's the electron domain and molecular geometry of ClO2 minus? Well, let's think about something real quick. So we have 3 atoms total. So this is either going to be linear in terms of the molecular geometry, or it's going to be bent. Those are the only 2 possibilities for having 3 atoms. So I mean, we can kind of rule out trigonal planar. We can rule out, well, that's the only one we can rule out. Trigonal planar. We don't have enough atoms for it to have a trigonal planar molecular geometry. And so in terms of the geometry, I got to go Cl. So let me count electrons real quick. 7 for chlorine, 2 times 6 for the oxygens, plus 1 for the minus charge. That gives me a total of 12 plus 8 for 20 electrons. And so that's going to be O, lone pair across. And then that's 16 electrons. 4 electrons left over go on to the central atom. And so this molecule here has to be tetrahedral domain because we have 1, 2, 3, 4 domains. You could argue if you make a double bond here, but it doesn't change the number of domains, it's still being 4. So if you want to make a double bond and do this to minimize 1, 2, 3, 4, 5, 6, 7, minimize the charge of chlorine down to 0, you still have 4 domains. It's still tetrahedral. It doesn't change anything with the geometry. So no matter what structure you're looking at, you have a tetrahedral molecule like water, and this is bent. And it's certainly not linear. So tetrahedral domain, 4 domains. So 1, 2, 3, 4 domains on the molecule, and bent for the molecular geometry name. 49, approximate bond angles. Well, C, let's start with C first. This is trigonal planar, so this would be about 120 degrees. This molecule here is tetrahedral, sp3. That one for C is sp2, by the way, in terms of the hybridization, if we were asked about that. B is tetrahedral, sp3, close to 109.5. And the same thing for A. So A is also tetrahedral, also sp3, also close to 109.5. So A and B 109.5, C 120. Looks like answer C. So let's look at polarity, BRF. For a diatomic molecule, if their atoms differ electronegativity, then the molecule has to be polar. So fluorine's more electronegative. This is like F2, but with bromine. So we have a single bond, polar, fluorine becomes more partial negative, bromine more partial positive. And so definitely, so if a bond's polar and the molecule's diatomic, then the molecule has to be polar. If a molecule has more than 2 atoms, then we have to think about the geometry of the molecule, we have to think about the shape, we have to think if the bonds are canceling each other out. For BRF3, this is 7 times 4 for 28 electrons. So this is a central bromine, 3 fluorines, lone pairs on the Fs. That's 24 electrons. The 2 electrons left over go on to bromine as lone pairs. And so this molecule here is T-shaped. And is this molecule polar as a result of being T-shaped? The answer is yes. So this molecule is polar. If it would have been like trigonal planar, then it would have been nonpolar, like BF3. But it's not trigonal planar, it's T-shaped, so this molecule is polar. BRF5, so that's 7 times 6, that's 42 electrons. And so that's a central bromine, 5 fluorines, and then a lone pair. So this is square pyramidal. Electron pairs opposite a fluorine. We have a buildup of negative charge behind the molecule here, definitely polar as well. So all these molecules here are polar. So 1, 2, and 3 are polar. Move on to 11. If we know a compound is XO3 and it's 60% by mass oxygen, what is the identity of the compound? Well, the identity of the compound can come from its formula weight, the percent O, given that we know that there's three O's, is going to be 3 times 16.00 AMU divided by whatever the formula weight is of this compound times 100%. That must be equal, in this case, to 60.0%. So let's get rid of the 100. Let's go to 0.600. Cross multiply the formula weight. Our formula weight is equal to 3 times 16, and then divide by 0.6. So 3 times 16 divided by 0.6 is about 80. So 80 AMU is the entire formula weight of the compound. Let's subtract the 3 times 16.00 for the three oxygens, and that's 32. So the AMUs of X is 32. That corresponds to, we can check a periodic table, to about the mass of sulfur. So this would correspond to being SO3. So number 12, compound is 87.7% carbon, 12.3% hydrogen by mass. It has this molecular weight. I've seen people solve this a few ways of kind of like breaking this mass up into this and trying to work out the number of carbons or something. There's more than one way to solve this problem. The way I think about this problem, though, is the systematic way of taking the percent by masses to an empirical formula. So going 87.7 grams of carbon to 12.3% grams of hydrogen in a ratio, using their molar masses to go to moles of carbon, molar mass of hydrogen to go to moles of hydrogen. Then we get the ratio of the moles of carbon within a sample. So we have 87.7 divided by 12, that's 7.31. And then 12.3 divided by 1.008 is 12.2. These are the ratios of the moles in a 100-gram sample. Well, let's just come up with their simplest ratio or try to get there, divide by the smallest. So 12.2 divided by 7.31 is 1.67 moles of hydrogen present in a ratio to 1 mole of carbon. And so we start thinking, okay, do we double? Times 2 doesn't work, it's 3.3. How about times 3? That works. So we go times 3 here for both of them. So C3 H 1.7 times 3, so 1.67 times 3 is 5. So the empirical formula we get from the percent by mass is C3H5. Now this corresponds to being 12 times 3 plus 5, that's about 41 AMU. We divide 41 into the formula weight of the compound. So 164 divided by 41 is 4. So we have 4 units in the empirical formula in this compound. So it's C3 times 4, H5 times 4. So C12, H20. This question here is looking at a limiting reactant problem. So in this reaction, which reactant is limiting when we have this quantity of reactants added together? How much of the excess reactant remains after the reaction proceeds to completion? Okay, so the way I might work this problem out here is to say, well, how much of the one do I need to react given all the other? Let me figure out how many grams of the calcium carbide I need to react with all of the water that we have present. Molar mass of water, 18.02 grams per mole of water. For every 2 moles of water that react, we can have 1 mole of calcium carbide react with it. The molar mass of calcium carbide is about 40.1 plus 12.01 times 2. It's about 64.1 grams. So 1 mole of calcium carbide, 64.1 grams. And so if we work this out here, 22.5 divided by 18.02, so that's about 1.25 moles of water, divided by 2 times 64.1 is 40.0 grams of calcium carbide. Let me double check my thought process here real quick. Let me make sure. 22.5 divided by 18.02 divided by 2 times 64.1. Just double checking out. So 40 grams of calcium carbide. So this is too much. I've consumed more of the calcium carbide than I have available. So we can't do that. So water cannot be the limiting reactant. So calcium carbide has to be the limiting reactant. And so then we figure out how many grams of water are needed to react with all of the 22.5 grams of calcium carbide. So it's 64.1 grams per mole. For every 1 mole of CaC2, we produce 2 moles of water. And then 1 mole of water is 18.02 grams. So to react 22.5 grams of calcium carbide, that's only 0.35 moles times 2. We need 0.7 moles of water to react with it, times 18.02. That's 12.65 grams. So 12.65 grams of water, this isn't the water mass remaining, this is the amount of water that reacts with this mass of calcium carbide. So we had 22.5 grams of water present, minus 12.65 grams that reacts. So 22.5 minus this quantity is 9.8 grams. Let's round that to 9.9 grams remaining. So calcium carbide is a limiting reactant. This problem is kind of weirdly worded, because it says which reactant is limiting, and so calcium carbide is a limiting reactant. Water is the excess reactant, and then 9.9 grams of water remains. When 2.5 moles of calcium chlorate dissolves in water, how many moles of ions are present in the solution? Well, this goes to calcium 2 plus, but then the question is, well, what does this go to? And the answer is chlorate. That the chlorate doesn't fall apart any further. Like we stay with chlorate, so our polyatomic ions generally stick together. And so we're going to end up with 3 moles of ions for this compound whenever it dissolves in water. So 2.5 moles dissolves times 3 moles of ions per mole of calcium chlorate gives us 7.5 moles of ions in the solution. So for every mole of calcium chlorate, we get 3 moles of ions, so 2.5 moles gives us 7.5 moles. Which compounds partially ionize in water? So this means which substance is a weak electrolyte. Weak electrolytes could be weak acids or weak bases. NH3s are prototypical weak base, so it reacts in water to partially react with it to form NH4 plus and hydroxide ion, just not to completion, so we have an equilibrium here. And then acetic acid has an equilibrium in water to form acetate ion, and then H plus. And so anything we learned how to name acid that's not one of the 7 strong, remember our 7 strong are HCl, Br, and I, NO3, ClO3, and ClO4, and then the first H off of H2SO4. So chloric, bromic, hydroiodic acid, nitric, chloric, perchloric, and sulfuric acid. And so we have a weak acid in the case of acetic acid. So both A and B here. Which term describes this thing here? Now this could be confusing in a way, but this is just ethanol. If ethanol were an acid, we would have called this probably something like ethanolic acid or something had a name acid. This H is not acidic. None of the H's are. For example, only this H off of acetic acid is acidic. These other hydrogens stay on acetate ion, even if you add strong base. They're not falling off of the carbon atom. So ethanol is neither an acid or a base. It's a non-electrolyte from water. So most of our molecular compounds that dissolve in water are non-electrolytes. The only ones that are electrolytes are acids, and it's just a matter if it's a strong or weak acid. And then the weak bases, like ammonia. You could also have things like NCH3 ammonia for like trimethylamine, triethylamine, triphenylamine, but these are kind of hard to spot. But it's just really nitrogen compounds serving as our weak bases. And then strong bases are already water soluble as being strong electrolytes. So our strong bases are things like calcium hydroxide, sodium hydroxide, things that are already classified as being water soluble as part of water-soluble ionic compounds. So our strong bases are strong electrolytes. 17, what is the molarity of H3PO4 in the solution here? So we have a solution of H3PO4. We're titrating it by adding KOH, seeing how much we need to fully titrate it, probably with some sort of indicator to indicate the end of the reaction. And so our concentration of H3PO4 before we start this titration would be the moles of H3PO4 initially present, divided by the volume of the solution. The volume of the solution is the 20.0 milliliters, 0.0200 liters. So we already know the volume of the solution here. How many moles of H3PO4, though, are there? Well, we get that from the KOH that's needed to titrate it. So if we multiply 0.0535 milliliters times 0.248 moles per liter of that solution, we get the number of moles of KOH. So we have 0.01327 moles of H3PO4, moles of KOH that are present in this quantity here. So these quantities here, 0.0137 moles of KOH, and then for every 3 moles of the KOH that had to be added means that there was 1 mole of H3PO4 present for that triprotic acid. So 3 moles to 1, so divide by 3, and so I get 0.00442 moles of H3PO4. And so I'm just taking this quantity here and dividing it by 0.200 liters to go to moles per liter. So divide by 0.02, I get 0.221 moles per liter of H3PO4. So that'd be answer D. So for 20, which statement is true when 4.75 grams of magnesium reacts with excess oxygen according to this reaction? And so less than 0 here, so exothermic, heat's being released by the reaction. So heat is being released by this reaction, not absorbed. So when 4.75 grams of magnesium reacts, what's the Q reaction? So the Q reaction would be 4.75 grams of magnesium. Let's go to moles. It's 24.3 grams per mole of Mg. And then according to the reaction, for every 2 moles of magnesium that reacts, the Q reaction is minus 1204 kJs. So the Q reaction is 4.75 divided by 24.3 divided by 2 times negative 1204. Q reaction is minus 118. So 118 kilojoules is released. So notice the sign flip's positive because we're saying how much heat is absorbed or released. 118 kilojoules is released. So this implies the minus sign. So he's being released when the Q reaction is negative. Let's look at a Q reaction positive in number 21. So ammonium nitrate, the delta H is greater than 0, so heat has to be absorbed by the reaction in order for this to take place. Where does the heat come from? The heat comes from the reactants or it comes from the solution. And so this solution that the reaction takes place in is the surroundings of the reaction. The temperature of the surroundings should go down when this reaction takes place because the heat of the reaction is going up. The heat's taking the heat from the surroundings. So the solution temperature should drop because the reaction absorbed some of its heat. All right, so the solution temperature would rise for exothermic reactions. Like if you took the reaction number 20 and say, well, what answer for number 20 would be true? So you said, okay, which of these answers would be true of 20 when the reaction takes place? The temperature should rise because the reaction releases heat from its reactants into the solution. So D would be the one consistent with number 20's reaction being exothermic. Okay, for this one, we have ammonium nitrate added to a coffee cup calorimeter, 125 grams of water, initially at 25 degrees C. What is the temperature of the solution if the enthalpy of the solution is 25.7 kJs per mole? The specific heat of the solution is out of water. Assume the calorimeter materials aren't absorbing much of this heat or aren't related, they have a negligible heat capacity. Okay, so what this means here is that the Q of our reaction is the negative Q of the surroundings, and the surroundings is the negative MCS delta T of our solution. Let me rewrite this one other way. Let's say our surroundings is the solution. The solution is negative MCS delta T. So the mass of the solution, CS of the solution, delta T of the solution. Q reaction is the heat of the reaction occurring inside the calorimeter. So the Q reaction here, we can actually calculate because we know the delta H of solution is 25.7 kJs per mole of ammonium nitrate. And we can even convert to per gram, say 1 mole of ammonium nitrate. It's 80.05 grams. So take 25.7 and divide it by 80.03. And that's actually, so that would be 0.321 kJs per gram. Well, we got 3.50 grams undergoing this reaction. So my Q reaction is times 3, 0.963 kJs. It's equal to 963 joules. Sorry for that. And so 963 joules is my Q reaction. That's equal to negative M of the solution. M of the solution is 128.5 grams. I'm doing negative mass of solution. And then CS of the solution, 4.184 joules per gram Kelvin. And then my delta T. Let's solve for delta T. So let's divide by negative 128.5. Let's divide by 4.184. All right, let me double check something. I know a number is not quite right. So 25, let me go back to this number here. Maybe this was off. 25.7 divided by 80.05 times 3.5. Okay, I think I did times 3, not 3.5. So this should be 1,124. I was thinking that number looked off. Okay, so then we do this math. So 1.124 kJs, 1,100 joules, 1,124 joules. Then divide this by negative 128.5, divide by 4.184. That gives me a delta T of negative 2.1 degrees C or 2.1 Kelvin. So the delta T, degree C, delta C, Kelvin, same unit. So we're going down by 2.1 degrees C. So our delta T is negative, the temperature is dropping. Endothermic reaction temperature of the solution should drop. So the solution temperature shouldn't go up, it should go down. It goes down by 2.1 degrees C. So that's 22.9. Is a photon absorbed or emitted when an H atom goes from n equals 5 to 2? So it looks like this. We go 1 to 2 to 3 to 4 to 5 to 6. So we're approaching infinity. N equals infinity. We're approaching some nominal energy. So 1, 2, 3, 4, 5. So 5 to 2 is corresponding for hydrogen to a drop in energy. So energy is being released from hydrogen when it undergoes this transition So energy is emitted in the form of a photon by an H atom undergoing this transition. So energy is emitted, and then if you're in tune with this being in the visible region, so this should emit a visible photon because the 6 to 2, 5 to 2, 4 to 2, 3 to 2 emissions of hydrogen are in the visible region. So this should be a visible photon. So this is going to be an emission at 434. The emission at 304 doesn't make sense, and then absorption doesn't make sense. So if we go from 2 to 5, we can absorb this photon, but not from 5 to 2. So to go up in energy level means we absorb energy, maybe a photon. If we go down in energy, we release energy, possibly in the form of a photon. If we wanted to calculate this, we would just calculate our delta E from, the E as a function of N is minus 2.18 times 10 to the minus 18 joules times 1 over N squared. So you just take this for the final state 2 squared minus negative 2.18 times 10 to the minus 18 times 1 over 5 squared, take the difference, convert that delta E from E is equal to hc over lambda to a wavelength, you'll see that you get 434 nanometers. Chromium has electron configuration 4s1, 3d5. So 1, 2, 3, 4, 5, 6 unpaired electrons. How many orbitals are in a 5p subshell? 1, 2, 3. 5px, 5py, 5pz. So 3. An orbital has an n of 4, m sub l of minus 2. What are the possible values of L? Well, when n is 4, L could be equal to 0, could be equal to 1, could be equal to 2, could be equal to 3. Now the range of m sub L is from minus L to 0 to plus L. So the only range of m sub L for 0 is 0. The only range for 1 is minus 1, 0, and 1. And so only 2 or 3 could have an m sub L of minus 2. And so this could be a 4D or a 4F subshell. So it could be L of 2 or 3. Which atom below has the greatest effective nuclear charge? So effective nuclear charge increases left to right, and we get a slight increase from top to bottom. Left to right increase because our core electron count is constant. They only screen charge from each other, and so we get an increase in effective charge from left to right. This is why size decreases from left to right. Then we get a slight increase from top to bottom because our core electron screening is becoming poorer the larger they are, and so slight increase from top to bottom. And so the greatest effective nuclear charge is going to be highest for iodine. So highest from left to right, and then from top to bottom, so it makes I higher for this group here. Now our size, the radius, our size is decreasing from left to right, and then increasing from top to bottom. So our largest atoms are going to be on the left side of the periodic table at the bottom. And so if we kind of reconstruct our periodic table, that sodium here is clearly going to be the largest because we're the furthest to the left and the furthest to the bottom, which are ranked by size correctly in 26. So we have an isoelectronic series. These all have 10 electrons. And so the more protons, the smaller. So magnesium should be the smallest, followed by sodium, followed by F minus. Looks like A. So we're looking at 12 protons versus 11 protons versus 9 protons in the nucleus of these ions from the number of protons pulling in the same number of electrons. So more protons for the same electrons makes magnesium 2 plus smaller. What is the general trend and explanation for first ionization energy from top to bottom? We get a general increase from top to bottom because of the increase in size. So as atoms increase in size, it becomes easier to remove an electron. So the ionization energy decreases from top to bottom because of the increase in size. This goes despite the increase in effective nuclear charge. If the effective nuclear charge dominated this trend, you would expect IE to increase from top to bottom, but generally it's decreasing. And this might be better stated that IE is generally decreasing because of this general increase in size. counterbalancing or being a bigger impact than the increase in charge or the effective charge increasing. Which ion contains the most unpaired electrons? So unpaired electrons, we have to sort of think that for something like zinc, 0 being a 4s2 3d10, that by rule we remove the largest electrons first. So this is a 3d10 for 0 unpaired electrons. Cobalt 0 is a 4s2 3d7, so we move these, we go to a 3d7. So we have 1, 2, 3, 4, 5, 6, 7, so we have 3 unpaired electrons. We go to iron 2 plus. Iron 0 is a 4s2 3d6, so we move these. We go down to having 4. Manganese is the good one. So manganese, if you want a lot of unpaired electrons, manganese 2 plus comes from a 4s2 3d5 for manganese 0. So move these electrons, we go to a 3d5. So that's the most number of unpaired electrons we can get here. That's going to be 5. Calcium has 0, just has a noble gas configuration. So manganese here with 5 would be the highest. Lattice energies become greater with smaller ions. So lithium chloride is going to have the lower lattice energy, or excuse me, the higher lattice energy, and then followed by sodium, followed by potassium. So we want the smallest, followed by the medium. So it looks like this one here. So the smaller the ions, the closer they are together, the harder and more energy it takes to separate them. Melting points for ionic compounds often found to be proportional to their lattice energies, which compound below would be predicted to have the highest melting point. So the highest melting points want the highest lattice energy. And so our lattice energy 2 plus, 2 minus are going to be the highest for A and B, plus 1 minus 1 for C, plus 1 minus 1 for D, plus 2 minus 1 for E. So magnitudes of charge are highest for A and B, and then MgO has smaller ions than CAS. So being smaller is better for a greater amount of energy to separate those ions, greater energy, higher melting point. So MgO presumably would have a higher melting point than CAS. 26, we get a sig fig problem. So we just have to apply the arithmetic and the sig fig rules in the order we do our calculations. So we do multiplication first. So that result is good to 3 sig figs. So I do 7.045 times 0.545. That's good to 3 sig figs. I divide by 0.0042. So that result here is good to 2 sig figs. So I get 914, but to 2 sig figs. Then I can add to that 6044, and it's all about where when we add that we're good to the tens placeholder. So we're adding 914. We could have rounded this to 910 if that makes it look better. It's not going to change the answer. And then I do 6044. And I line up my placeholders and I round to 6954. So I'd round this to 6,950 for 3 sig figs. I'm having a memory that I circled 2 sig figs on the key, so I'll have to double check the key for this one. But 3 sig figs for this one here. 27, or 27, number 5, which has the most neutrons. So our mass number is the sum of protons plus the number of neutrons, because those are the 2 particles that carry the most mass in an atom. So an atom with an atomic number 28, so that would be nickel. So a nickel 59, 28 would have 59 minus 28, so that's 31 neutrons. For A, B has manganese with a mass number of 55, so an Mn 55, well, the mass number, or the atomic number is 25, so element number 25 from the periodic table. The difference here is 30 neutrons for this manganese atom. Iron 56 is Fe56. Iron is element number 24, so this is 32 electrons. So 56 minus, I'm sorry, iron is element number 26. So 56 minus 26. So I'm just looking at a periodic table, element number 26. So this is 30 neutrons. And then chromium 52, chromium is element number 24. 52 minus 24 is 28, I think. 52 minus 24, you have 28 neutrons. So they all don't have equal neutrons. D has the least. B and C have 30. A has 31, so A has the most. Some elements exist, like iodine is only one isotope, and it exists as iodine 127. What's the atomic weight of this isotope? Well, all we need to do is check the periodic table. Check the periodic table for I, it's 126.90447. Just looking at a periodic table, we get answer C. You may wonder, how do you know this? How would you know that iodine exists as one isotope? Well, you look at iodine in a mass spectrometer. So we determine abundances and the more exact atomic weights of isotopes using mass spectrometry. Last question here is some naming. So this is potassium carbonate, sodium chlorite. That's one fewer than the 8. And then this would be Fe3 plus, O2 minus, so Fe2O3. And then magnesium sulfate, Mg2 plus, SO4 is a 2 minus, so MgSO4. All right, so that's the remaining problems from the lecture review set of problems. One more time, good luck on the final, and I'll see you guys around.